here. This is video 10.1 on the history of motion theory. And in this video, we're going to talk about the scientists in the past who had different ideas about how things move and why things move and by what rules do things move and how that relates to what we know about motion today. So we're going to start back in ancient Greece with our old friend Aristotle. And as you might remember, he also came up with a theory about matter, about what everything is made of. And he was the first person in our history of atomic theory. And he theorized that everything is made of earth, fire, wind, and water, these different elements, not the same elements that we have on the periodic table. Well, he also had a theory about motion because he was basically the most respected philosopher of that day in 400s BC. And he said that with regards to motion, there is this idea of telos, which means goal, and that everything is moving to this ideal state. It's not as it's supposed to be, it's moving towards the perfect. And in addition, he applied this idea of telos to motion and said that objects move towards their highest goal, even if they're not alive, even if they're just an inanimate object. And the implications of this theory were that, in his theory, heavy objects move down and light objects move up. Now, this isn't so unreasonable, right? Because in our everyday experience, we see things like rocks fall down, but helium balloons actually move up. So this was his theory to explain that idea. He also said that force was required to keep objects moving and that they wouldn't just keep going on their own unless there was a force acting on them. He also said that heavy objects fall faster than light ones. So we are going to look at these implications and see if they hold any water in the future, but they do kind of make sense on first glance. So now we get to Galileo Galilei, who came thousands of years later in the 1600s, and he showed that objects actually fall at the same rate regardless of mass. So we're going to talk a lot more about that experiment and how that worked. He said that the distance fallen when you drop objects is proportional to the square of the time, and that makes sense from what we know of acceleration, which is meters per second squared, same idea. He proposed that force is not required to maintain a constant velocity. And he also accepted this idea that the sun is at the center of the solar system, which we know to be the case now. But at the time, everybody thought that the Earth was at the center of the solar system and that the sun and other planets rotated around the Earth. So Galileo was one of the first people to popularize the idea. It's called the heliocentric theory, where helios means the sun is at the center. And let's talk about that a little bit. Okay, so let's go back and look at these in a little bit more detail. So objects falling at the same rate regardless of mass. So let's do a little experiment in real time. And I have here, and these are my Bluetooth headphones. They're kind of heavy. And I also have a piece of paper right here. So if I were going to do this experiment, and I would ask you guys, if I dropped them at the same time, which would hit the ground first? So think about that for a second, and then we're going to try it. All right, ready? Go. Oh, would you look at that? The headphones actually fell a lot faster than the paper. The paper kind of did this business. Other people have done this experiment with a hammer and a feather. Okay, so why would that be the case? Because this almost looks like Aristotle's theory was right, that heavy things fall faster than light things. Is that really how it works? Well, what if we were to crumple this paper up? It's not going to change the mass any, right? It's only going to change its shape. It's still just as light as it was. So I'm going to crumple this paper up and see if it falls at the same rate. Okay, so if I crumple the paper up, it's actually going to fall at the same acceleration as this guy. So that might lead us to believe the reason that the paper or the feather, whatever we're using, does this kind of business is not because of its weight, but because of air resistance, which is another force that is pushing up on this paper and keeping it from falling at the same rate. It's not because of the mass, it's because of air resistance. And in a few, maybe 50 years ago, astronauts went to the moon. This is the last time that human beings were actually on the moon, which is kind of exciting. And now here in 2023, they're talking about sending human beings to the moon again. But it's been a long time since they've been there. So the next video I'm going to show you was an astronaut who set foot on the moon and repeated this experiment that Galileo did. Because what Galileo did is he took two objects, a heavy ball and a light ball, and threw them off the Leaning Tower of Pisa, which is a famous tower in Italy that kind of leans. But he threw them off at the same time and showed that they hit the ground simultaneously, even though one was much heavier than the other one, but they had the same shape. So that negated the effect of air resistance. It didn't let if you tried this with a feather, then air resistance is a problem. Anyway, the astronauts did this on the moon, and let's see what happened.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Okay, that is so cool. So on the moon, there is no atmosphere. And so, of course, that shows us that the only thing that is keeping the feather from falling at the same rate is air resistance. All right, so that's just so cool. It shows us what, if we remove the air, then a hammer and a feather are going to fall at the same rate. So this brings us to our final scientist in this series of history, and this is Sir Isaac Newton, who took what Galileo started and really put it into a systematic set of laws. So Isaac Newton has 3 laws. You need to know them, and they're called the first law, the second law, and the third law, and you can't mix them up, okay? So the first law says that objects in motion tend to stay in motion. Objects at rest tend to stay at rest unless they're acted on by an outside force. Now, you know this to be true already in terms of human behavior, right? If you're in the middle of a video game, you're in motion, and you're like about to accomplish some great feat in this video game, and your mom says, hey, stop playing, it's time for dinner, you don't want to stop, right? Objects in motion tend to stay in motion. Your mom's going to have to like put some force on you to say, hey, if you don't come to dinner right now, I'm going to take your phone away, in order to get you to move and to change your course of action. Conversely, objects at rest tend to stay at rest. So today is a weekend day, and I like to sleep in the morning, and it's hard to get me out of bed because objects at rest tend to stay at rest unless acted on by an outside force. So I've got to have my like kids banging on my door, Mom, I need you to get me something, in order to get me out of bed on a weekend morning. The same is true when we talk about objects that are moving. So if you launched a satellite into outer space and it's now going at a really fast velocity, say, 2,000 kilometers per hour, it's going to stay going at that constant velocity forever and ever, unless it's acted on by an outside force. So the only way to get it from moving at that velocity is either by firing a rocket or launching something else that hits it, that changes its direction or changes its velocity. And usually it's by firing a rocket that's on that ship. Otherwise, it will go forever. And that's kind of counterintuitive. That's not what Aristotle said previously. He said that you can't keep it going at the same velocity unless you put a force on it. But that turns out not to be the case. The only way that you can get it to change its velocity at all is by putting a force on it. So it's counterintuitive, but it works when you consider how things work in outer space. Okay, Newton's second law is force equals mass times acceleration. And in the next video, I'm going to show you how to solve that equation, which is very useful. And it's kind of putting into mathematical terms what we said in the first law, that the only way to get something to change its state of motion, to change its velocity, is to put a force on it. And changing its velocity means it's accelerating. And that force is proportional to its mass. So the heavier something is, the more force you need to put on it to get it to accelerate. All right, and then last but not least, we have Newton's third law, which is for every action force, there is an equal and opposite reaction force. So what that means is that right now I'm sitting on this chair, and because I have a mass and there's a force on me due to gravity, I am putting a certain amount of force on the chair. However, that force, that chair is putting the same amount of force right back on me. And if it weren't, I would fall to the center of the earth. So whenever you're standing on the ground, you're putting a force on the ground because you have a mass, but the ground is also putting a force right back on you, equal and opposite. You're putting a force on the ground's putting a force back on you. If it weren't putting that force on you, you would fall to the center of the earth. So it's a good thing that we have a solid ground to stand upon. So you need to know these three laws. The other example I like to give for the third law is if you've seen that movie WALL-E, which is a very fun movie. There's a scene in there where WALL-E, the robot, is just floating in outer space and he has a fire extinguisher. And the only way he can get himself to move is by firing the fire extinguisher. So if he blasts the fire extinguisher that way, which way do you think he's going to go? And the answer is equal and opposite direction. You could try this too at home. If you are sitting on a skateboard and you fire a fire extinguisher, it will blast you in the opposite direction, because for every action force, there is an equal and opposite reaction force. That's all I have for this video. I'll see you in the next one. Have a great day.